Hello everyone, welcome to my YouTube channel, Effective Coder. Today I'm solving Leetcode question 1293, shortest path in a grid with obstacles elimination. You are given an m times n integer matrix grid, where each cell is either 0, 0 indicates empty, or 1, 1 indicates there is an obstacle in the cell. You can move up, down, left, or right from and to an empty cell in one step. So you can move in the four directions. Let's say you have a neighboring cell and then the cell is an empty cell. You can move up, down, left, or right. So return the minimum number of steps to walk from the upper left corner, 0, 0, to the lower right corner. The coordinate is m-1 and -1, given that you can eliminate at most k obstacles. If it is not possible to find such walk, return -1. So let's take a look at the example. In the example 1, so we have a grid, m times n, m equals 4, n equals 3, and then there are 4 obstacles on the grid in total. So it specifies that k equals 1, which means we can eliminate at most 1 obstacles. So let's starting from the starting point and then trying to move to get to the end point. So starting from here, we can move down, move right. So basically, you can check all the 4 directions to see if there are cells you can move to. If it's empty cell, you can move there. If it's an obstacle, you can move there only if you can eliminate that obstacle. Let's say, in this case, our k equals 1, so you can move here by eliminating this obstacle. What if k equals 0? In that case, it's not possible to move to this cell because you cannot eliminate an obstacle. You just hit the obstacle here. So in this case, we can move right and move down. Let's say we eliminate this obstacle and move down. And then we just continue this path. It's all empty cells after that. And then we can reach to the end. It takes us 6 steps. So that's actually the shortest path. So it's the 6th. Let's say, what if k equals 0? If k equals 0, you cannot eliminate any obstacles. You are forced to take a longer path. That is, by getting around all the obstacles and walk on the empty cells. In that case, you take this reversed S-shaped in order to get to the end. So, but in that case, you still have a possible path to get to the end. Let's take a look at example 2. In this case, you got 6 obstacles on the grid, and then your k equals 1, which means you can eliminate at most 1 obstacle. It's not possible for you to reach the end from the starting point, because by traveling in any directions, it requires you to remove more than 1 obstacle. So in that case, we just up the -1. So we understand the problem. Now let's talk about how we are going to solve it. So it's for any shortest path in the unweighted graph, we always utilize BFS. So why BFS works? Because the first one reach destination is one of the shortest paths, as each move is 1 step in BFS. So BFS, you are moving to the neighbors. Basically, the move along each path is in the same speed. So some paths have more steps, some paths have less steps, but in utilizing BFS, every move is the same step. Every move is 1 step. You are moving along all different paths in the same speed. So that's why the first one reach the destination is the shortest path. Let's say if you have a longer path, and then when you reach the destination on the shortest path, you are still somewhere in the middle way of that longer path. Because remember, every time when you move the same step. So every move is 1 step. Along all the different paths, you are moving at the same speed. That's why BFS can be utilized to solve the shortest path problem. So what is the time complexity here? So the time complexity is m times n times k. Why? Worst case scenario, we have to visit a cell k times to try different obstacle eliminating options. Similarly, in that case, the space complexity is m times n times k. For BFS, you need to utilize a queue. In the worst case, you need to visit a cell k times, so you need to add each grid with the corresponding k value or obstacles left to eliminate into the queue. So that's why it's m times n times k times for the space complexity. Now let's take a closer look at the time complexity, m times n times k. Why need to visit the cell k times? So let's say for this example, looking at this cell, we can just travel from the starting cell, moving right, moving down to reach this cell. Along this path, we do not need to eliminate any obstacles except for the obstacles in this cell grid, in this grid cell itself. So the total number of obstacles eliminated when you reach this cell is 0. When you pass this cell, it's 1. However, if you take a different path, let's say traveling from the top cell, moving down and moving right. In this case, you already encounter one obstacle before you reach this cell. So in that case, after pass this cell, you need to eliminate 2 obstacles. So you can see that there are different number of obstacles left. So in the worst case scenario, we have to visit a cell k times. After discuss the idea, let's start coding. So we first get the dimensions for the grid. And then we initialize a queue utilizing the Python DQ. And then we add the starting point to the queue. So what does this represent? It's row index, column index, and then steps, and then obstacles left to eliminate. We also need to keep track of all the cells we have already visited. So in that case, our visited equals set. What is tracking? It's tracking the row index, column index, and then the obstacles left to eliminate. Why don't we want to visit the same row, column, obstacles left to eliminate more than once? So because if we have already visited them in the previous steps, so we know that path is shorter than this one with the same row index, column index, and obstacles left to eliminate. So we don't want to repeatedly visit them over and over again. So let's start visiting the queue. So while queue, we pop the row index, column index, the steps, the elimination left from the queue. And then we check, let's say if row index equals m minus 1, and then column index equals n minus 1. In that case, you already reached the ending point. You just return the steps. If we are not reaching the ending point, so we just check the neighbors, like all possible directions or next steps we can move to. So in that case, we check the neighbors. For the neighboring index, okay, so those are all the neighboring index. And then you need to check to see if they fall within the boundary of the grid. If it falls within the boundary of the grid, then we can potentially move to that cell. So in that case, let's check the value inside that cell. If it's empty cell, so and then you haven't visited that cell before, so in that case, you can just directly go to that cell. In that case, you just append it to the queue. And then you also need to track it's already visited. Remember here, we only update the steps. So basically, by moving to the neighboring cell, moving from our the position RC to position NRNC, you move one step. So that's why we need to update steps plus one. You did not utilize any obstacle elimination because this cell is already empty cell. So you keep the same number of obstacles left to eliminate. If this grid cell is an obstacle, and then here you need to be able to update. So basically you need to have your elimination greater than 0. You need to be able to eliminate. So if this cell is an obstacle and then you do not have anything left to eliminate, let's say your k starting with the k value k equals 2, and you already use up all the 2 possible eliminations you can use along this path. No more obstacles are left to eliminate. So you cannot eliminate any more obstacles. In that case, I mean, you cannot visit this cell. You can only visit if you still have eliminations left. So in that case, the elimination is greater than 0. And this one, after you eliminated this one, it should not be in visited cell. So in that case, we just append that to the queue and visited. So in this path, remember, we eliminated one obstacle. So that's the elimination minus 1. After checking all the possible cells that we can visit, basically after emptying out the queue, if we still cannot reach the destination, which means we did not return, in that case, we just return minus 1. Let's have to run the code. Okay, we get a working solution that passes all the test cases. So it's only faster than 20% of Python 3, and they utilize less than 23% of Python 3. Let's see how can we actually optimize this solution a little bit. So let's take a look back at this solution. So there is one optimization trick you can do. Let's say before even getting into the queue. Let's say if I have unlimited obstacle elimination. So basically this means, like, let's say if we can have unlimited obstacle elimination. So no matter how the configuration is, so basically your k value is greater than the is greater than or equal to m plus n minus 1. In that case, you just return m plus n minus 2. So why m plus n minus 1? So let's go back to the description. So in this case, let's say you need to travel from the starting point to the end point. So the dimension, the number of rows is m, the number of columns is n. The shortest path, the optimal one, let's say if you do not have any obstacles, is to take a direct path without any detour. So traveling down, going to the right, that's one possible shortest path. In that case, the total number of steps is 6. That equals m times n minus 1. So basically, let's say if you have the number of obstacles to eliminate, that's kind of greater than or equal to the length of the shortest path. That means even if you fill out this shortest path without obstacles, you can still reach to the destination point. So in that case, that's kind of our optimization. Let's try to run the code. Let's try to submit it. Okay, in that case, it reduced the runtime from over 1000 to 120 milliseconds by utilizing this trick. Now let's take a look at if we can further optimize this one even further, or utilizing some other approach. So the main idea still stay the same, still utilizing BFS. So I'm going to actually tweak this visited set a little bit. So in that case, let me see if I can save a little bit memory. So let me keep track of visited matrix. So I create a matrix called visited, and then it's the same dimension as my original grade. So it has m rows and n columns. I initially filled this matrix with value -1. And I will tell you later why I fill this one with -1 at the very beginning. And let's try to comment out this one for now. And then let's say we are not utilizing visited to keep track of that. So in this case, uh, let's say we are still traversing. Basically, we still pop from the queue. And then if reach the endpoint, we just return the steps. If not, we just contemplate our next move by checking the neighbors in the four directions. And then if we still need to check if it's within the boundary. And then after that, I'm going to make some modification here. So in this case, let's take a look. So if the grade nr nc let's say, what if my visited nr nc if my visit nr and c, the value of that is less than the elimination. In that case, which means like, okay, right now we have another path that we can traverse through this grid with a better strategy, let's say a better elimination option. So in that case, we just update it. So, okay, so what are we trying to do here? So let's say, okay, we check all the neighboring cell. For this neighboring cell, NR and NC, and then basically the values on this neighboring cell is how many elimination need to be left in order for me to pass this cell. So if this cell is possible, then the number of eliminations needed has to be less than the number of eliminations we have. So because remember, why less than? Because remember, we haven't eliminate the obstacles on this cell yet if it has an obstacle. So in that case, we append the NR and C and then the steps +1 and then the current number of eliminations to the queue. And then we mark this one. Basically, we say that, so okay, we find a better path. That's we find a better path, and then with the more eliminations left. So in that case, we just update that one. So we do the obstacle updates here. This solution actually saves a lot of memory. Let's combine this with the previous optimization strategy we utilized. Okay, we get more memory optimization. Why? Because for this visited, this dimension is only m times n. So the overall worst case complexity still can be m times n times k because we are constrained by this q, but we save a little bit on this visited set. So in that case, we save a little bit memory. So now let's take a look at this solution again to see why it works. So basically, in this one, we just utilize a visited matrix to keep track of, okay, for each cell, for all the paths that can pass the cell, so the obstacles left to eliminate, or the obstacles, the eliminations required to pass that cell. So we still pop the from the top of the queue, and we check if we reach the destination. If we reach, we just return steps. And then when we pop this one, let's say if this grade is actually an obstacle, we update our elimination value. So in this case, we did not update within the neighboring when we visit the neighboring cell. So that's why when we pop it up, we just do the updates. So okay, so if the current cell, we are visiting the current cell, and if current cell is obstacle, we just reduce the number of eliminations left, and then we check the neighboring cell to see if we can pass to the neighboring cell. For the neighboring cell, if the visited, let's say the elimination needed is less than the current elimination we have. So currently we have this elimination left. So basically, it means we can still eliminate this number of obstacles. In that case, this path is a possible path. We can pass from here. So we just add that to the queue, and then we update the this visited matrix, update the value to the elimination, because we have a better or possible path compared to what we had previously. So that's why we will utilize that for our later traversal. Let's say, let's take a closer look at this with an example. Let's say when you can also see that why we initialize this to -1, because the k is actually greater than or equal to 0. So initially, when we first encountered, we just update this one with the actual number of k, or number of elimination left. So this visit -1 is always less than the elimination during the initial visit, the initial encounter. So during the initial encounter, we just updated with like, okay, what is the number of obstacles left to eliminate when we reach this point, when we reach the cell NRNC. So that's kind of the overall strategy for that one. So let's say, take a look at the example. Previously, the number of visited is for this NRNC is 2. And right now, we have the elimination value 3. So, which means, okay, previously, some paths visited this cell NRNC, and then during that visit, so we already eliminated, we just have 2 eliminations left. So if we continue traveling down that path, we can only eliminate 2 more obstacles. So in that case, now we have a better path. So in that case, we just update this value to be used for later paths. So later another path, let's say, visited this cell NRNC. So that's kind of why we are updating this one. So that's the end of the video. In this video, is quite long, so I talk about 2 different solutions that I utilize to solve this problem. So I think the first approach is more intuitive and easier to understand, but it utilizes slightly more memory. The second solution is a little bit, I would say, it's a little bit hard to grasp the idea at the very beginning, but it's actually saves some memory. So that's the end of the video. If you like my video, please subscribe to my YouTube channel. Thank you.